Yes.
Okay, awesome. And then I guess I went and I looked in a book. And so to answer Theo's question about the coefficients, like the interpretation of the H star coefficients. And so I kind of will talk about this in a little bit, but if you have a simplex, so any polytope can be triangulated into simplices. And so, which is the moral of the story that I'm going to share in a little bit. But if you have a simplex, the H sub I coefficient of the H star polynomial counts the number of integral lattice points in the fundamental parallelepiped where the last coordinate is the ith position of that H polynomial, or the H star coefficient. And so if you don't know what the fundamental parallelepiped is, it'll come out in just a second.
Cool, cool. Okay. Thanks, Andrés, for that was the question from the pre-seminar. So let's welcome Andrés again. He's going to give us the seminar part of the talk. Yeah, take it away, Andrés.
Awesome. And so I'm going to first, so again, just to say again what I'm going to do, I'm going to show two generalizations of the two generalizations of the decompositions of the H star polynomials that hold for lattice polytopes, and we'll do it for rational polytopes. One of them is due to Betke and McMullen, and one of them is due to Stapledon. Okay. So first, some setup and notation. A rational pointed simplicial cone is a set of this form, where this bold W is a set of linearly independent vectors in Z to the D. And I'm going to define the open parallelepiped associated to my rational pointed simplicial cone to be this box of W, which is of this form. And one thing that I need is this projection. So I'm going to project, or I'm going to let U be the projection onto the last coordinate, where from there we define a box polynomial to be the sum of this Z to the U of V, where the V are the number of integer lattice points in my box. Okay. And you might say, Andrés, this is all notation. I don't understand it. So it's okay. Don't be afraid. Here's a little example. And so here's W. Let's take W to be 1, 3, and 2, 3. Then this is what my box looks like. Okay. And you might be able to visualize it. But if you have a hard time visualizing things like I do, sometimes it's better to write them down. So here's my, again, 4th grade rendition of this box. And so notice that this is an open box. So I'm not counting any of the number of, I'm not counting any of the integer lattice points on the boundary. So this box only contains 2 interior lattice points, yeah? And so the box intersected with Z2 is 1, 2, this point 1, 2, and the point 2, 4. And so my associated box polynomial is Z to the last coordinate. So it'll be Z squared and Z to the 4th, okay? And so what is this box polynomial doing? It's kind of encoding or keeping track of the number of lattice points in this box. And so then the fundamental parallelepiped is the half-open variant of the box. So now we are including some of the boundary. And so it looks something like this, okay, for my last example. Okay. We also care about coning over. I mentioned coning over a little while ago of the polytope. And so for a rational polytope P with vertices V1 through Vn, we lift the vertices 1 dimension higher by appending 1 to the last coordinate. Well, I append it to the last coordinate. If you're using any computational software like Polymic and things like this, it'll append it to the front. It doesn't really matter, just whether you're looking at it like this or you're looking at it like this. And so this is what the cone is. And so here's a cone of my my rectangle from the pre-seminar. And the nice thing about working in the cone setting is that if you have the cone and you slice it by a hyperplane, an integral like hyperplane, you can recover the Qth dilate of the polytope. Okay. And so I also care about triangulating the polytopes, right? And so I said that the moral of the story was that simplices make life easier. And so I'm going to triangulate my polytope P into simplices, but I'm going to keep track of all dimensions, of simplices of all dimensions. And so what I mean by that is like, here's my rectangle P. And so I'm going to say, okay, here's my triangulation. And I have triangulations. I have simplices of 2 dimensions. So I will have 4, right? This one, this one, this one, this one. And then I'm going to keep track of all the 1-dimensional simplices. So all the line segments, which should be 1, 2, 3, 4, 5, 6, 7, 8, I think. And then these 0-dimensional ones, which are the vertices. So in this case, I have 5 because I'm choosing my triangulation to include also this interior point. And then I'm going to also keep track of the empty simplex. And similarly, dang it, I cannot speak English today. Similarly, how I define the denominator of a polytope, I'm going to define a denominator of my triangulation. And I'm going to define it to be the least common multiple of all vertex coordinate denominators of the faces of my triangulation. And so, for example, the difference between the denominator of P is like here I would only consider the vertices, but in this particular triangulation, now I also have to consider the LCM, keeping in mind this point here, right? And so that might change the LCM. Okay. Are there any questions so far? No? Okay, I'll continue. And so another thing that I need is this H polynomial. And so for each simplex in my triangulation, we define the H polynomial with respect to the triangulation as follows. And I don't really want to say much about it other than this exists. And if you are familiar with H polynomials, this is in fact the H polynomial of the link. Okay. But what is this polynomial doing? It's keeping track of the information, kind of like of the topology of my triangulation. Okay. And so for a simplex with denominator P, we're going to let W be the set of integral ray generators of my cone at height P. So remember, before we took things at height 1. Well, now we have to take things at height the denominator, right? Because we're dealing with rational stuff. And so I'm going to define the H-star polynomial of a simplex to be the generating function of the last coordinate of integer points in the fundamental parallelepiped. Okay. And so the H-star polynomial of the H-star polynomial of my simplex is just the generating function of the last coordinates of the points in my fundamental parallelepiped. Okay. So the decomposition a la Betke McMullen, I'm going to take P to be a rational polytope with the triangulation T that has denominator Q. For an amp simplex in my triangulation, I take R sub I Q to be the integral ray generators of the cone at height Q. This is just setting some notation. Instead of writing out box of W, I'm going to say box of the simplex or the box polynomial of the simplex. And so here's a lemma. I'm going to fix a triangulation T with denominator Q of a rational D polytope. And I'm taking all the simplices in T, and I'm going to say, then the H-star polynomial of a simplex is the sum of the sub-simplices, if I write them as half-open decompositions. So I'm taking the box polynomials of the half-open decompositions of my simplex. And so, oh, did I not have a picture of that? Oh, I think I took off the picture. My bad. Oh, that's sad. Okay, maybe. The idea is now, okay, so you have a half-open parallelepiped. And so like the one
Can I just ask Andrés then, is the union of all of the omegas precisely delta, or is there some overlap? Like by taking them half open, do you make sure that the union is exactly all of delta, or are there still overlaps?
I'm taking them half open because the union is exactly all of delta, and then I wouldn't have to deal with over counting lattice points if for some reason they share something. So and maybe if I can scroll a little bit back here, right? Here's my half open parallelepiped, and so I would take maybe the whole thing to be empty as one part, then I would take this part to be one, and then this part to be one, and then just this vertex to be another part. So I'm just kind of decomposing it into half open things. Okay. Hopefully, I used to have a picture there, and for some reason I didn't put it in this time. Okay. So what is my decomposition? The generalization of the Betke McMullen is saying the H star polynomial is in fact just the sum of box polynomials and H polynomials. And so this is what it looks like. You might say, well, that's okay, Andrés, that's okay. But I'll tell you why it's kind of cool. First, note that box polynomials are just keeping track of the arithmetic data coming from the simplices, or for the integer points in the simplices, right? Or in the, I should say, not simplices, but the parallelepipeds. Now, each of the coefficients of the H star of the box polynomials are all just one. So what we really are caring about are whether or not the H polynomial is non-negative. And it turns out that the H polynomial is non-negative. And so when we're multiplying, this is kind of just shifting things in the H polynomial. And so these should all be sums of things that are non-negative. And so from here, we can already deduce Stanley's non-negativity result. Okay. Now, why do I like it? Again, this is bringing together, things that are keeping track of the topology of the polytope and the arithmetic data of my triangulation. Okay. Are there any questions? No? Okay. So I'll give you a proof sketch of how this works. I'm going to write my polytope P as a disjoint union of all open non-empty simplices.
I'm sorry, Andrés. I would like to ask a minor question. So you're phrasing the theorem with all of the authors. Is there a difference in the exact statement in the lattice case, or is it like the same exact statement in lattice and rational cases?
It's different because now we have to worry about lifting this to height Q. And so the difference is we now have this Q popping up, and my H polynomials will also look different because I'm not, again, I have to keep track of these Z to the Q.
I see. Okay. Thank you.
So the proof, well, I guess I should not lie. I have never really seen Betke and McMullen's original proofs. I won't speak to that, but the proof that we have here, I think, is the same spirit. So we write P as a disjoint union of all open non-empty simplices in the triangulation. And so what does that mean? Each of these non-empty simplices have an Ehrhart series, right? And so then I use Ehrhart-McDonald reciprocity, right? Because there's some relationship between things, counting things that are in the interior and things that are not. And then I apply the previous lemma, right? Because I'm now dealing with each of the individual simplices, and I know what the individual simplices look like in terms of their H polynomials. The box polynomials are symmetric, so they have some symmetry. There's some natural involution that I kind of left out because those are just minor details, but there's stuff there. And so I use that symmetry to my advantage, and then I use the definition of the H star polynomial, and I obtain my result. So this is a kind of a gross oversimplification of the theorem, but this is the steps of the idea. Okay. But the cool thing is now we are able to write down a proof for Stanley's monotonicity result. And so to repeat from earlier, what Stanley's monotonicity result is, if you have P contained in Q, which are rational polytopes, with the Q dilates of each for some minimal possible Q such that these things are now integral, and I define the H star polynomials to be like this, then the H star polynomials, the coefficients of the H star polynomial of Q dominate the H star coefficients of P coefficient-wise, okay? And so what does that look like? Well, let's take this tetrahedron as an example. Let's take Q to be the three-dimensional thing, and P to be the two-dimensional triangle in the bottom, okay, the bluish thing, yeah? And so here I computed the H star polynomial of Q, and here I computed the H star polynomial of P, and again, coefficient-wise, these things dominate the lower blue, okay? That's what this result is saying. Okay, any questions? No? Okay. I think me adding that picture clarified a lot, I think. And so this lemma, which I won't prove to you, but it really is the big work of the result. but I'll state it. So again, I'm supposing P to be a polytope and T to be a triangulation of P. I'm going to take P to be contained in Q and T prime to be the triangulation of Q, such that when I restrict myself to P, that triangulation is T, okay? And when I was originally thinking about this, I kept on ignoring the fact that my smaller polytope P could be lower dimensional. I was always taking things to be full dimensional. So here's the intricacies of these things. So if dimension of P is less than the dimension of Q, I have to assume that there exists a set of affinely independent vertices of Q that sit outside the affine span of P, such that the join of T with the convex hull of those vertices outside the affine span of P is a subcomplex of T prime. And the dimension of P join the convex hull of those vertices is exactly the dimension of Q, okay? And I will say, or maybe you're wondering, how will our proof be different than Stanley's original proof? I always have a challenging time reading over Richard Stanley's original proofs because they're very algebraic. And so I will say that his original proof was strongly algebraic. So my hope is that this one's at least a little bit more discrete geometrical, even though this lemma relies a little bit on some underlying things in Cohen-Macaulay stuff that I really just learned just to prove this lemma, because I am not an algebraist by any means. And so for every face omega in T, the coefficient-wise inequality holds, okay? And so what is this saying? This is, again, showing just the monotonicity of the H polynomials of the triangulations. Okay, so this is the real big bulk of, or the work of this result. Okay.
Andrés, can I ask you, this assumption that you made on the triangulation, can you always construct two such triangulations that that satisfy these assumptions and this determinicity?
Yes, I believe so. I think that you can always do this. And I have, for example, maybe just a picture here to kind of illustrate this. Because, well, yeah, I think that the answer is yes. I won't say anything more than that before I get myself in trouble. So here's Q. Q is my hexagon, and I'm going to triangulate it. So here's T prime, which is the triangulation of Q. And so P is this line segment. And in this particular example, maybe because it's a little small, I can take the triangulation to be the polytope itself, okay? And notice that T prime restricted to P is T, okay? And so what is this saying? It's saying that the H polynomial of T prime will dominate the H polynomial of T, okay? Awesome. And so here's Stanley's result again, and let's do a proof sketch. This is, again, the setup that we mentioned earlier. Okay, so T prime restricted to P is T, which is a triangulation of P. By my rational Betke McMullen result, I know that my H star polynomial of P should be of this form. Okay. Since P is contained in Q, I can write the H star polynomial of Q. Thinking about it, well, there's the stuff concerning P and then everything else outside of it. Okay. By the lemma, the coefficients of each of these corresponding parts dominate one another. Okay. And so if I put all the pieces together, and again, I'm going kind of fast because there's a lot on this screen. I hope that I convey that it really is just putting the pieces together. So I'm taking the smaller stuff with P, and then I'm splitting Q up to be the things with P and the things without P. And then I'm just putting these inequalities together, okay? Okay, and that is essentially Stanley's monotonicity result, really just coming down to the dealing with the triangulations. And so I really hope that that I convey that this is more discrete geometrical than Richard Stanley's original algebraic proof. Great. And so that ends our first decomposition. And so now I want to talk about the decompositions coming from the boundary triangulations. And so just to make sure, it's 2:51. How much more time do I have?
10 minutes.
Okay.
We started a bit late. Is that okay?
That's perfect. Yeah. I mean, we started a little bit late before me. So the next thing is I'm going to talk about a decomposition coming from a boundary triangulation. Okay. So again, I have to do some setup. I'm going to fix a boundary triangulation T with denominator Q of a rational polytope. And in this setup, or in this construction, I'm going to take L to be some positive integer such that the L dilate contains a lattice point A in its interior. And so when I cone, such that this point A comma L is a point in the interior of the cone of P, okay? And so when I cone over A comma L, that's literally just a integral ray, or I shouldn't say integral ray, it's a ray through the point A comma L, okay? So we cone over each of the simplices in the triangulation, and again, we define our integral ray generators to be R sub I Q, where these are things now at height Q, okay? And so the difference here from the last setup is that now we have to care about this specified point A comma L, okay? And so I'm gonna take W prime to be the set of integral ray generators of my cone union that point A comma L, okay? And so each of these, the W and the W prime have associated box polynomials, okay? And maybe I'm gonna skip over this because it's not just too many details. So what is the composition say now? So I'm gonna consider a rational D polytope that contains an interior point A over L. When we're in the cone and we make everything big, we can say A comma L. And we fix a boundary triangulation T of P with denominator Q, then the H star polynomial looks like this, okay? So this is just the H star polynomial. And it's a sum of these box polynomials coming from things where I care about that specified point A comma L and the stuff that doesn't, okay? And we're multiplying it by, and it turns out that you have to multiply by this rational form here. The beauty of this is that it always simplifies, okay? And so I'm showing you this decomposition, but I really want to use this decomposition, okay? But before I do that, I want to show you an example of how this thing works. So I'm going to let P be just this small line segment 1/3 to 2/3, which is this little line segment over here, okay? Again, maybe we fall into the trap of small dimensional examples. So I hope that I convey this thing, but it is a small example, I understand. So this is the line segment 1/3, 2/3. I'm going to take the cone over it. And so I have to, this is the orange here is the cone of 1/3, 2/3, okay? What is my, I'm taking a boundary triangulation with denominator 3, right? The denominator is the LCM of the all vertex coordinate denominators. I'm going to specify a point inside the interior of the cone. So I'm going to choose 2/4. I mean 2/4, 2 comma 4. So here's 2, 4. That's the point that I'm choosing, right? The blue is the cone over this point 2 comma 4. So I took a boundary triangulation, and in a line segment, the boundary triangulation is not that interesting, but we do have the empty face and the two vertices, 1/3 and 2/3. Here's W1 and W2. You could ignore that for right now, but here's the collection of information now that I need, okay? Notice, and so what is the difference between this construction and Stapledon's original construction is, because we have rational stuff, we have to worry about getting things big enough to become integral again, right? And so in his original case, when he specified a point A comma L, or what I'm calling A comma L, this cone never contained any lattice points. Now, in our case, we run into the situation where we sometimes have lattice points, okay? And so here's all the information that I needed, and I'm putting it together, and now it's, you know, you put it all together, and that's nice, and this is what you get in this particular case, okay? You might be wondering, Andrés, well, how is this construction more helpful? I don't know computationally if it is more like, I haven't run any experiments, but that's something to look into. But for lower dimensional things where we're trying to construct things by hand, it seems to work quite nice. It's not that difficult to do, yeah. But I guess one goal would be to look at this more experimentally. Okay. Okay, I have 3 minutes left, and so I'll share this proposition. So if P is a rational polytope with denominator Q and has this Ehrhart series form, then the degree of the H star polynomial is S if and only if this thing here is the smallest integer dilate of P that contains an interior lattice point, okay? So in a sense, here we're able to tell, we should be able to tell at what point we should be having an interior lattice point in some dilate, okay? Why is that important? Well, because next I want you to turn your attention to this polynomial, which I call H star bar. And all I'm doing is I'm moving the denominator. So let's go back here. All I'm doing is moving this denominator to this side, okay? And that's what I'm calling H star bar, okay? And so a theorem here is that H star bar has this unique decomposition, which we call an AB decomposition, where L should look familiar. It's that first point where we see an integer lattice point in the dilate, right? But the nice thing about this decomposition is that this A polynomial and this B polynomial have integer coefficients, and they're symmetric, okay? So that's quite nice. And they're non-negative. So they're symmetric and non-negative. Okay, so I think this is quite nice. And so from this, when in the pre-seminar, I mentioned that one open problem in Ehrhart theory is to classify all Ehrhart polynomials, right? Or H star polynomials equivalently, right? Because it's just a change of basis. We could make that question a lot broader by asking, can we classify all Ehrhart quasi-polynomials or all H star polynomials coming from Ehrhart quasi-polynomials? What does that mean? Well, that means that maybe we have to put some restrictions, right? Because it's very challenging. We might have to fix a dimension and or fix a period, right? But again, if we don't even know it for the lattice case, it's going to be even harder for the rational case, I imagine. So towards that classification, maybe one nice thing to ask is, are there any inequalities that are satisfied by the coefficients of the H star polynomial? And so from this theorem, we actually do that. And we get that the H star vector, if I'm just taking the vector to be the collection of the H star coefficients, they satisfy these inequalities. And this first inequality, I think, generalizes a result by Stanley, and this one generalizes a result by Hibi. I might have gotten that the other way around, but in any case, they really fall nicely, and they both did it separately, but they were both on the right direction to getting it themselves, or both themselves, but they each did one separately. And so what we contribute towards that classification is some inequalities that are satisfied by the H star coefficients of that thing. And so I'm 1 minute over, so I'll just tell you real quick what that one application. So for a lattice polytope, it's called reflexive if its dual is a lattice polytope. Okay, and so in 92, Hibi said that if a lattice polytope is a translate of a reflexive polytope, if and only if this equality holds with Ehrhart series as rational functions. In other words, P is a translate of a reflexive polytope if and only if the H star polynomial is palindromic. Okay. In 2008, Fissett and Kaspczyk proved that a rational polytope P, whose dual is a lattice polytope, has palindromic H star polynomial. And what we prove is that if we have a rational polytope containing the origin, the dual of a polytope is a lattice polytope, if and only if the H star bar is exactly the H star polynomial, meaning that the B of 0 in my AB decomposition is always 0. Okay. And so to answer even before, from the very, very, very first thing that I said in the pre-seminar for the example that I gave, why that was palindromic, if you do the AB decomposition for that thing, you should be, for that example that I showed earlier, you should be getting that B of Z is in fact 0, which tells us that we should be expecting a palindromic H star polynomial. And with that, I think I'll end. Gracias.
Thank you, Andrés, for this lovely talk. Let's thank Andrés, everybody.